So, good evening, everyone. Welcome to the first week live interaction session for the course Bioelectrochemistry. So, let's just wait for a few minutes for others to join before we begin our session for today. So, as it's the very first introduction live interaction session, so I request you guys to basically uh, introduce yourself, tell your name, and what you are currently pursuing, and why you opted for this bioelectrochemistry course. So you can either unmute yourself and then speak up, or you can also type it in the chat box. Yeah, good evening. Oh yeah, good evening. Sorry, my mic was in mute. I didn't realize that. So, oh, okay. So you are So Aditya is a research scholar and he's kind of pursuing tissue engineering to revise the concepts of electrochemistry and that. Okay. Oh, okay. And why specifically the course on bioelectrochemistry? Just a second. One. Yeah, okay. So without any further delay, let's start our session for today. So let me just share my screen. So I hope my screen is visible and I am audible. Yes, anyone? I hope there is no disturbances from my side. Okay. So let me introduce myself. So, good evening, everyone. I welcome you all to the very first live interaction session for the course Bioelectrochemistry. This course is offered by Professor Mainak from the Department of Biological Sciences and Bioengineering, IIT Kanpur, under the NPTEL program. Myself, Pratyumnan, a PhD research scholar in the Department of Chemical Engineering, IIT Guwahati. I am the course team member. I will be conducting the live interaction session for this particular course in the Jan to May 2026 semester. So this is a very short, you can also say it as a crash course, which is split in 4 weeks, covering almost around 20 lectures. So the very first live interaction session will be mainly focused on basic concepts related to bioelectrochemistry, or more to be specific on electrochemistry, and then after which we will progress towards understanding about galvanic cells. So to start with, the live interaction session that we will carry out on that we will be meeting on every Saturday for the next 4 weeks, including today. So we will have a brief recap, or you can say a review on the course content for around 30 minutes, and the rest of the time will be allotted for solving some of the problems, either in the form of MCQs or as a numerical problems, so that it will be helpful for solving your course assignments, which you will have to submit every week. So the very first session is on the basic concepts of bioelectrochemistry. So here in the audience, how many of you are aware, or how many of you are kind of familiar with the concept of electrochemistry, or have any idea on what electrochemistry really is? Any past experience with electrochemistry? Of course, electrochemistry we do have studied it in our school level. So, other than that, any kind of experience with electrochemistry during UG or PG, or if you are a research scholar, any experience in the electrochemistry domain? Okay, so electrochemistry as such, if you see, you can split it into two different words. It's electro plus chemistry. That is, we have uh, electricity as well as chemistry, electric current as well as chemistry. So it is kind of a subject of study where we deal with both the electrical concepts as well as with the chemistry concepts, or you can say we discuss more on the interface between the electricity as well as chemistry, or electrical and chemical. So we see how both of these domains are interrelated to each other directly or indirectly, and that is what we are going to study here also in the term of electrochemistry. But here we try to study the electrochemistry something more specific towards biological applications, or you can also say to study how we can use these electrochemical tools for biological applications, how these electrochemical tools can be used for biological purposes. So in the recent days, if you see, for majority of the disease detection, or kind of for majority of these disease detection, or you can say, we there is this concept of wearable sensors. So we, for majority of the diagnostic purposes and other biological related applications, electrochemistry is becoming one of the major tools to make these process more easier. If you are familiar with the concept of wearable sensors, majority of these sensors which is used for detection of the hormones like cortisol or dopamine, all these kind of sensors use this electrochemistry as their fundamental principle for their working. So that is what is this course will be primarily concerned about. How we are going to use the knowledge of electrochemistry, or how these electrochemical tools can be used to study biological applications and solve the biological problems that are yet to be uh, s- that are yet to be identified, or which is there already, or which are solved. So that's what is this course is all going to be about, bioelectrochemistry. So this is a kind of a subject which deals with it, which is a very interdisciplinary subjects dealing with electricals, chemistry as well as biology. So we will try to correlate all the three and bring all of them in one particular basket. So before going on to deal with bioelectrochemistry, let's first focus on electrochemistry, understand their basic concepts, then later see how they can be useful for biological applications. So electrochemistry, if you see, is primarily used in majority of these energy storage devices. So your typical energy storage device as such as batteries, supercapacitors, and you can also say in energy harvesting you have fuel cells. So all of these energy storage as well as energy harvesting devices that I have mentioned use electrochemistry as their fundamental mechanism for working, or of working. So in case of these batteries as well as supercapacitors, for the people who are not familiar with electrochemistry, for them these devices seems to look like a black box. It seems like a particular box wherein, or particular device wherein you can actually store energy for some time, and then whenever you require you can extract the energy from this box and then use it for their application. But that but this is actually a kind of a major misconception, because the batteries or supercapacitors or any energy storage devices as in it itself is a major field of study. There are so many problems and challenges which are yet to be solved and also yet to be identified in the future. So they have enough potential to satisfy the demands that are present, but at the same time there are also a lot of problems within these batteries as well as the capacitor fields which are yet to be solved. So this is about a brief this thing on the course. To start with the basic concepts, I hope majority of you will know about how electricity actually, what is the typical meaning of current, right? So we say that, for us, for majority of us, if you turn on the switch, then there is a power, and then there is a flow of the current, and then your appliances start working. But how does that actually takes place? It's basically due to the flow of current. But so here we need to define current as a parameter. So that is what is the basic concept that we will first discuss. We will first try to understand the definitions of each of these parameters which are important, and then later let's talk about the galvanic cell. So the first term is current. How do you define current? So there is a interaction session. So if you are aware of the definitions, then you're always welcome to unmute your mic and then share your responses. Okay, flow of electrons. That is correct, but it is, sorry, flow of electrons. But I want the complete statement. Flow of electrons is fine, but again, it does have certain other. It's not a complete definition. It's partial. The flow of electrons from one point to another per unit time, is it the, does it actually make the definition of the current? Flow of electrons, or you can say charges. So this is how we define current. So this is a very well known definition. So might be the language might have been twisted, or might have been expressed in different way, but that is what is the exact meaning. The how much charges, or the flow of the charge at a specific point over a specific period of time is called as the, is how you actually measure current. Now, since we have described about flow of electrons or flow of charges from one point to another, there comes a question on why there is a flow. What is the major driving force which is causing these charges to move from one point to another point? So that is the major driving force is nothing but it is called as the potential difference or the potential gradient. So gradient is nothing but it's basically the difference. So why there is the flow of electrons. So these concepts again, as also mentioned in the course by professor, they may seem to be something that is already been discussed or learnt over in the past, but for for the better understanding we try to recollect them so that our basics becomes clear before we progress towards understanding of the other complex cells or complex electrochemical cells to be specific. So next comes the flow of charges happens due to potential difference or due to a potential gradient. Is it fine? Now, so when there is a potential difference, the flow of charges will happen. So if you take for example point A or first point, and if you take for second point, so between these 2 points there will be a flow of charge, but then but how to determine whether that flow of charge is going to happen from 1 to 2 or 2 to 1, or if you take 1 as material A and 2 as material B, material A, and then the second one as material B. So how the flow of charges will happen, whether it will happen from 1 to 2 or whether it will happen from 2 to 1. So so here the answer lies in the work function of the particular material. Is it fine? I mean, so if I ask what do you mean by the work function, can anyone tell me what does the work function of a material actually means? Yes, flow of charge between two materials typically depend upon the inherent property of the material. That is the work function of the material. But what exactly does the work function of a material mean? Because once we know which has a greater work function, then we can start thinking, then once we get to know that, we will be able to tell whether the charge is going to go from 1 to 2 or 2 to 1. And then if suppose if it is going from 1 to 2, or let's say the material A has a greater work function compared to material B, then the flow of charge from A to B will be more spontaneous compared to moving the charge from B to A. So that is going to be an energy intensive process. When I say energy intensive, it typically means that I have to put more amount of energy and more amount of effort in order for that particular process to complete. So the question is, what do you exactly mean by the work function of a material? Yes, anyone? Work function. Oh, mm, oxidation potential, oxidation state. Yes, so you can say that it typically work function as such. The major kind of you can say the exact definition is the amount of energy that is required to remove an electron from the material. So if material A has it also, as someone said, how easy the material can actually give away the electron. That is what is actually the work function typically means. So if the material A is able to easily give away the electron, then moving the charge from material A to B will be easier compared to moving it from B to A, because because material A has more greater tendency to lose its electron. So that particular process of moving so that particular process of moving the charge from A to B will be more easier. That process will be comparatively more spontaneous compared to moving the charge from B to A. That will typically require more amount of energy. It will be an energy intensive process. So I'll write here. So depending upon the work function, you can determine whether the movement, depending on the work function, movement of charge or electron can be determined. So in case of these biological systems, such flow of charges is going to be very common, is going to be very predominant in fact, and that is typically due to proteins. So if you see in case of the mitochondria as well as chloroplast, their mitochondrial membrane typically has more amount of proteins, or are usually covered with the protein structures. So these basically causes a kind of this actually generates the potential difference which causes the flow of the charges in them. So bioelectrochemistry, you can also consider it as a kind of a concept where we can also try to study about the flow of the charges through the biological systems as well. So this is about current, which is nothing but flow of charges across a specific point at a particular time interval or a time instant or over a period of times or over a time period. Now this flow of charges happens due to the potential difference or the potential gradient, and whether and when there is a flow of these charges between two, when there is a flow of the charges between two materials, the work function of them typically determines whether the charge will move from A to B or B to A. Now, with respect to this flow of charges, there are two different processes. Again, you are very familiar with this. One is the oxidation and another one is the reduction. So oxidation is nothing but donating or losing electrons, and the reduction is nothing but accepting the electrons. So in terms of electrons, if you say oxidation is nothing but you donate or you lose the electron and get oxidized to a more positively charged species. In case of the reduction, you accept the electron and then reduce to a lesser positively charged species. So this is about oxidation and reduction. Again, this is a very basic, this you might have learnt in your school level itself, oxidation reduction processes in terms of electrons, the redox chemistry specifically. So when both this oxidation and the reduction happen together, we call those kind of reactions as redox reactions. Oxidation and reduction occurs simultaneously. So here my question is it always necessary for an oxidation and a reduction reaction to happen together, or only oxidation can happen and only reduction can happen? As such, in a general process, is it possible that, or is it always necessary for both these reactions to happen simultaneously, or one particular reaction can happen independently of the other, like as two different entities or reactions? Can this happen? Any idea on that? No. Okay. But are there not any systems where oxidation alone has happened and reduction alone has happened? And okay, if so, if you say that they cannot happen independently of each other, why is that so? Anyway, I'll put this as discussed in next class, but still try to search on this particular aspect, whether only oxidation and only reduction reactions are possible. If no, as someone said, if they have to occur simultaneously, then why is that so that they have to occur simultaneously? What is that will be violated if they start happening independent of each other? So this I'm going to keep it for, I'm not going to discuss this right now. Now we have learnt about oxidation and reduction. So the species that actually donates these electrons and then loses, or donates or loses these electrons to form to become a more positively charged species is called as an oxidized species. And then the species that accepts these electrons to form a lesser positively charged species is called as a reduced species. Again, here I'm saying lesser positive. It can also happen that it can become negative as well. So do not take that. You can understand. I am sure. So oxidize the species and reduce the species. Now, what? So this is about oxidize the species and reduce the species. So in this case, what is actually the meaning of an oxidizing agent and a reducing agent? You can also call oxidized species as an oxidant and a reduced species as a reductant. But what is the meaning of oxidizing agent and reducing agent? Yeah, so oxidizing agent is nothing but which oxidizes something, which oxidizes its next component and reduces itself. Similar way, reducing agent is the one which reduces the other species and oxidizes itself. So it's just like complementary to each other. Someone rightly said oxidizing agent is the one which actually accepts the electron and oxidizes the other. Yeah, that's fine. So this is about the basics of you can say the very basic concepts of electricity, current electricity, you can say. Now we will discuss about more on this galvanic cell. So here I'll also discuss about the other concepts like free energy, voltage and etc. So galvanic cell is nothing but it's an electrochemical cell. So there are actually two types of cell. One is an electrochemical cell and another one is an electrolytic cell. So in case of an electrochemical cell, the chemical energy is converted to electrical energy. Whereas in case of an electrolytic cell, electrical energy is converted to chemical energy. So can you give examples of an electrochemical cell and an electrolytic cell or electrolytic process as an electrochemical process and an electrolytic process? Yes. Any examples? Of electrochemical cell and electrolytic cell. You actually don't need to give this I mean, if you give me the reaction, that is fine. Electrochemical reaction and electrolytic reaction, let me write it that way. Lithium ion batteries, okay. Gold plating process, yeah, those are correct. Another thing is, in case of the electrochemical reaction, fuel cell is a good example. And in case of electrolytic reactions, you can say water splitting, H2O. If you actually pass electric current, you can generate hydrogen gas and oxygen. And similarly, that process can be reversed. In case of a fuel cell, hydrogen and oxygen, hydrogen gets oxidized and oxygen gets reduced to form water, and it generates electricity. So there, the chemical reaction drives the or the chemical reaction generates electricity. Here the electric current drives the chemical reaction. So that is the typical difference between an electrochemical cell or an electrochemical reaction and an electrolytic cell, sorry, or an electrolytic reaction. So chemical energy is converted to electrical energy, and here electrical energy is converted to chemical energy. Energy has to be converted from one form to another. It can neither be created nor be destroyed. So this is based on which law of thermodynamics? So here energy conservation happens. If you see these systems, the electrochemical systems, there is a energy conservation. So which law of thermodynamics states that energy can neither be created nor be destroyed, but it can be converted from one form to another? First law of thermodynamics, yes. So, coming to talking about galvanic cell. So galvanic cell is an example of electrochemical cell. So here the chemical energy is converted to electrical energy. The chemical reaction happens, and that actually give rise to electricity or electric current. So the redox reactions, what we typically discussed about, there is a flow of electrons in them, and that flow of the electrons is what is helping or that flow of the charges is what giving rise to electric current or electricity, and that is what we harvest and then we store them. So in case of fuel cell is a great example for energy harvesting devices. As I said, the hydrogen H2 molecules undergo oxidation to form H plus ions and releases the electron. These electrons moves towards the cathode, and the oxygen consumes this H plus ions and the electron, resulting in the formation of water molecules. And in this process, the electron flows from the anode to the cathode. That flow of the charges give rise to current, which we harvest and then store it for the later use, or you harvest the energy for your necessary needs, and at the end you have a byproduct which is nothing but the water, and that water is one of the most purest form of water that you can obtain from a particular process. But again, the amount of the yield of H2O will be very less due to a lot of different losses, and also the amount of energy that gets generated or the current that you can extract will not be very high. Again, that is typically due to the losses that happens within the system. It's again one whole area of research. So there are several different components which needs to be optimized in order to reach to the potential that it can actually deliver as per theory. So, so that is what the thing is. The redox reaction, there is a flow of electrons or flow of charges from the anode to the cathode, and that flow of the charges leads to electric current, which we can harvest for a particular need. Now, so this galvanic cell is also called as a Daniel cell. So the architecture of this particular galvanic cell goes in this way. So you have the zinc electrode and you have the copper electrode. The zinc electrode is dipped in zinc sulfate solution and the copper electrode is dipped in copper sulfate solution, and these two chambers are separated by a porous disc. It's a semi-permeable membrane, so it allows only selective flow of ions through them. But again, it's a physical barrier that separates these two compartments, and that's how the reaction proceeds. Okay, so this is a typical way on how you actually represent this galvanic cell. The typical the representation style should be this one: zinc, and then there is a vertical line, zinc 2 plus, two vertical lines, then copper 2 plus gives copper. So can anyone tell me what is the reaction that happens at the anode and what is the reaction that happens at the cathode? And more than that, how do you decide? Let's not look at the picture. Between zinc and copper, how do you decide which one undergoes oxidation and which one undergoes reduction? Because when you have two materials, one has to undergo oxidation and then the other one has to undergo reduction. That's how a complete electrochemical cell is formed, or that's how the electrochemical cell is formed, and that is the point where the electrical circuit gets completed and there will be a electricity that gets generated. So without the circuit being complete, you cannot expect electric current to be generated, right? So there should be the circuit should be completed. So between zinc and copper, how do you decide which one should be anode, or you can say which one should undergo oxidation and which one should undergo reduction? Don't see the picture because the picture says zinc as anode and copper as cathode. So I should have actually removed that, but okay, that's fine. So here, since zinc is an anode, we know that in anode the in anode oxidation takes place and reduction takes place at the cathode. But let's assume that this information was not available to us. So we are given two different materials, or let's say two electrodes, and then we are supposed to construct a cell. Now we should have an idea on how to determine which one is going to be the anode and which one is going to be the cathode. How to state this, or how to analyze this and then come up with a solution. Or you can also say what is that particular parameter that I need to consider to distinguish a material whether it should be a cathode or it should be an anode. Zinc will okay. Ashishta De. I hope I am not pronouncing your name wrong. Zinc will undergo oxidation, hence it will be anode due to high oxidative potential, and for copper due to higher reductive potential, hence it will be cathode where the reduction will takes place. So how do you actually tell this? I mean, uh, yes, that's exactly correct. That zinc has more oxidation potential, so that means it typically tends to undergo oxidation, or more preferable to undergo oxidation in comparison to copper. Copper has higher reductive potential, so it tends to undergo reduction. But how do you actually say this, that if zinc has more oxidation potential and copper has more reduction potential? Valency. Uh, okay, yeah, electrochemical series makes sense because valency as such, if you see zinc also has 2 plus and copper is also is having 2 plus, so that will not be a of any deciding factor. But yes, electrochemical series is right one. So based on that electrochemical series, we tend to decide whether a particular material has more oxidation or reduction potential, has more I mean, based on that particular series we can easily determine which material will have more tendency to undergo oxidation compared to other. So how many of you actually have an idea of that standard electrochemical series? You have actually, you actually know the, I mean, how many of you have ever seen that electrochemical series? The the elements in the electrochemical series with their value. Yes. Has anyone ever happened to see that particular electrochemical series chart where you will have a list of elements and then you will have their what do you say, the standard reduction potential values as well? No one, I mean, so yeah, you can go and, I mean, after this session gets over, I okay. Yeah, that is okay. So yeah, you I encourage everyone to actually go through that electrochemical series and then the standard reduction potential. One thing that what you would observe is all that values that you have in that electrochemical series will be written on the basis of the reduction potential. They will not talk about oxidation potential. Their values will be based on reduction potential of that particular element. Now I'm also curious, and I also want you, all of you whoever are here today, to actually go and see why is it that that particular uh, values are based on their reduction potential and not based on their oxidation potential. I mean, what is the primary reason for this chart being prepared in such a way based on the reduction potential of the element rather than the oxidation potential? Because if you see, all the elements over there will have their E value based on their reduction potential, not based on the oxidation one. So I hope I mean, I actually ask all of you to actually go through that electrochemical series and then try to find out a reason, if at all there exists a reason. There should be a reason. So try to find out that particular reason on why all these values are based on the reduction potential and not on the oxidation potential. So coming back to galvanic cell, yeah, so here uh, zinc has the tendency to undergo oxidation more compared to copper. So the zinc will be so the zinc will undergo oxidation, copper will undergo reduction, and since oxidation usually happens at anode, so zinc to zinc 2 plus will be that particular reaction will happen at the anode, and the copper 2 plus to copper will happen at the cathode. So shall we write the reaction? Can anyone tell me how to write this reaction? Anode reaction and cathode reaction. Zinc 2 plus 2 electrons, and so these 2 electrons will be transferred from the anode to cathode. There will be a flow of this electron. That flow of the electron will be harnessed. The energy in the that flow of the charges will be harnessed in the form of electric current. These 2 electrons will go and will enter at the cathode. So there Cu2 plus will accept these 2 electrons, forming copper, and that copper will actually get deposited at the surface of the electrode. So this is the reaction that will happen at the cathode, and this is the reaction that will happen at the anode, and this is how you typically represent the galvanic cell in terms of their electrochemical reactions, or how that electrochemical reactions typically progresses. Now so if you see here, I have a doubt. So the zinc will undergo oxidation and it will release 2 electrons. That is, it will donate 2 electrons. And then these 2 electrons will enter inside the cathode. That story is fine. But what happens to that fate of zinc 2 plus? That zinc 2 plus that gets generated out of this reaction, what happens to them? Basically, my question is, how does the circuit gets completed, or how does the entire reaction happens in this galvanic cell? Because we have to the flow of electrons is fine, but apart from that there are also other things that are happening within the system, and we are supposed to have an understanding on them as well. So that two electrons leaving from anode to cathode, and then the energy that gets generated, you harness that, that's absolutely fine. But what about that zinc 2 plus that gets generated in this compartment? First let's focus on the compartment, the anodic compartment, then let's talk about the cathode. But what happens in the anode, the anodic compartment, what happens to the zinc 2 plus ions that are generated in the oxidation reaction at the anode? Yes, anyone? Sulfate ions. But again, yeah, that I can get. So what do you mean is that zinc 2 plus whatever is there will combine with the SO4 2 minus, right? But already you have that, but in that particular electrolyte for that zinc 2 plus, let's say for every zinc 2 plus you have an SO4 2 minus ions. So you do not have excess of SO4 2 minus ions to compensate this particular zinc 2 plus charge. You have zinc sulfate solution. So that zinc sulfate, for every zinc 2 plus ions you are going to have, for every, let's say for example, one Zn zinc 2 plus ion, where you will have one SO4 2 minus ions, and they will be, I mean there will be they will be bonded. Now this zinc 2 plus whatever is getting generated is getting generated at the expense of the electrode. This electrode is going to undergo oxidation, releasing zinc 2 plus. So that zinc 2 plus, what will happen to that zinc 2 plus? You do not have that SO4 2 minus ion in the solution to compensate for this zinc 2 plus that gets generated. So the system, that particular anodic system, is going to become excessively positive over the period of time as the reactions keeps happening. So how to compensate that charge, that zinc 2 plus charge that gets generated? Any responses? Yeah. So the diffusion will typically happen across the chamber ion transfer. So that Cu2, as someone said, I think Aditya, he rightly said that there will be the diffusion of the ions. So which ions will diffuse? So in order to compensate for that zinc 2 plus charge, the SO4 2 minus ions that is there in this cathodic compartment will undergo diffusion through this semi-permeable membrane and then will enter inside the anodic chamber, uh, and then that zinc 2 plus will combine with that SO4 2 minus ions. Now, so the story of anodic compartment is clear to us. So since there is a diffusion, there is a mass there is a mass transfer between this cathodic and the between the cathodic and the anodic compartment. So the number of SO4 2 minus ions within this cathodic system is going to deplete. So you will have more amount of Cu2 plus ions within the cathodic compartment. So the problem that existed now previously in anode is going to get shifted to cathode. So there will be more Cu2 plus ions that will be present in the cathodic compartment now. These Cu2 plus ions will combine with these two electrons to form copper, and that copper will deposit on the surface of the copper electrode. So that's how the entire electrochemical system, or you can say the entire circuit, gets completed, or the entire redox reaction process happens within the galvanic cell. Here we do not add, again this is a system where there is no heat and mass transfer. It's a closed to be specific, it's an adiabatic system where there is no mass and heat transfer. So that's how we were able to write that the chemical energy is converted to electrical energy following the first law of thermodynamics. So here there is no mass, there is no addition of external mass or energy from outside. All the things that happens within the system. The zinc 2 plus whatever gets generated makes the anodic compartment more positive. In order to compensate for that, the SO4 2 minus ions from the cathode moves towards the anode and then neutralizes the anodic compartment. Due to this diffusion, the cathodic compartment becomes more positive, and this electrons whatever flows from anode to cathode reacts with this Cu2 plus ions, undergoes the reduction process to form copper, which gets deposited at the surface of the electrode. So this is the entire electrochemical reaction that happens in the galvanic cell. Now here there is a particular thing. The thing is basically this semi-permeable membrane that we were talking about. So can that be considered as osmotic diffusion? In osmosis, there will be the diffusion of salts, but again this particular question I have to look around whether this can be considered as an osmotic diffusion, because here there is only the movement of ions due to the ionic concentration gradient that gets generated. There is only the movement of the anions from one compartment to another compartment. You can say the diffusion, but whether that can be called as an osmotic diffusion, because in osmosis there is a pressure gradient that usually gets generated, due to which there will be the movement of salt molecules. But again, I will have to look at this question and then only I can let you know. I will take up this question probably by the end of this class. I hope if it's that okay. Yeah. So that particular porous membrane is something which is very important, because they physically separate these two compartments, but at the same time they allow the selective movement of certain ions. So this is again, it is indeed a whole area of research where people try to tune the molecules in such a way that they can actually um, change the tune the molecules in such a way that they can try to selectively make molecules pass through ions to pass through them. So that's again, it's a whole entire research area focusing on membrane development. Now again, there is another one. There are two questions that I have with respect to this galvanic cell, which I want you to think about, and if you have an answer, you are welcome to tell me. First thing is, as we have seen in at anode, the zinc is undergoing reaction. It is forming zinc 2 plus, and then that zinc 2 plus comes to the, I mean, comes outside, and I mean, that zinc 2 plus goes into the electrolyte. So that means over the period of time, as the reaction keeps happening, that zinc 2 plus is going to actually deplete. The zinc electrode is actually going to deplete as time progresses. But at the same time, if you see in case of the copper, that the 2 plus ions will keep reacting with that Cu2 plus, and then that copper is going to keep on, what do you say, keep on getting reduced and get deposited on the surface of the electrode, and that electrode is going to become thick as the time progresses. So what would eventually happen in this process? So does that mean that the cell will die after a certain time? Because anode is going to become thinner and thinner, and cathode is going to, that electrode as such is going to become thicker and thicker as the time progresses. So what will be the fate of the galvanic cell? That is the first thing. Second thing is, let's say that I remove this this membrane, what you see, this semi-permeable membrane that we were talking about. What will happen if I just remove them? What will be the fate of the galvanic cell if I remove that semi-permeable membrane? Whether the cell will work or will it not work, or if so, then why? I mean, what do you actually expect when you think about this particular mix of solvents? I mean, of these electrolytes. Porous membranes removal will lead to a short circuit. Okay. So again, think about this. Apart from short circuit, will there be any kind of other, uh, I mean, will the cell actually work, or whether are there any other problems which will arise when you remove this? Please have a look at it. Let's think about this, because it will take some time for everyone. So think about this, and this also, let's see it in the next class. So this is about galvanic cell. Again, apart from galvanic cell, you also have some type of cell based on cadmium and silver chloride. So those I'm not going to, I mean, that is already covered in the last lecture of our week 1 course. So please have a look at it. Now let's move towards solving some problems. So since this is the very first week, we will not deal with more number of numerical problems. It will be more of the basic concepts. So let's start looking at them one by one. So in case if you know the answer, you are welcome to unmute yourself and then explain that to all of us here, or again you can also type that in the chat box. So have a look at these questions and yeah. So let me read out the question first before you answer. So the question 1 is, in the reaction is x3 plus some x and y element, x3 plus y2 plus gives x2 plus y3 plus. Now here you are supposed to tell me which one is getting oxidized and which one is getting reduced, and as an additional question from my side, tell me which one will act as an oxidizing agent and which one will act as a reducing agent. So then which one will be the correct option? I mean among A, B, C and D? So as we discussed, let us write that reaction as well. So I will take this heat from this one and then I will going to just paste it here. So instead of writing oxidation and reduction, let me just write it as such. Before that, just a second. So x3 plus is getting converted to x2 plus. So which means 3 plus is going to 2 plus. So that means there should be a addition of an electron here. So in case if anyone is not able to understand, please let me know, because this will be important, because the entire electrochemistry is actually based on this. So if you have an understanding on this, then majority of the reactions that we will be discussing further in this course or in any kind of electrochemical processes that you take, they will, their fundamentals lies here. So if you have any doubts, then please feel free to ask. Similarly, y2 plus is, oh sorry, is giving y3 plus. That means there will be an electron negative charge here. So is the charge satisfying? 3 plus plus an electron, so 2 plus, and here also 2 plus means 3 plus plus electron, so that is fine. So as we know, oxidation means donating or losing of an electron. So y2 plus, so this particular process is oxidation and this one is reduction. So y2 plus is getting oxidized and x3 plus is getting reduced. So y2 plus is the oxidized species and x3 plus is the reduced species. So As far as this question is concerned, answer is C. So since X3 plus is getting reduced, it is the oxidizing agent, and Y2 plus is getting oxidized, so it is the reducing agent. So I hope there is not much confusion. So I will write it somewhere below. Because often people get confused with this oxidizing agent and reducing agent, so please be a little bit more careful when you actually go for these kind of questions. So the next question is, I hope there is no doubt related to question number 1. If you have any doubts, you are welcome to ask me. In case if you have no doubts, for those of you who do not have any confusion related to question 1, look at question 2. Which of the following is not present in Daniel cell? Daniel cell, again, it means it's a galvanic cell. So take the typical galvanic cell that we discussed previously. Based on that, you answer this one. This is going to be easy. It's just the component that you need to let me know. I think answers might have been there. HCl, yes. HCl is the one which is not present in the galvanic cell. Okay. So here again I want to actually kind of ask one more question to the previous two questions that I asked related to galvanic cell. So if you see, in case of this galvanic cell, we use electrolyte as salt solutions. So you are welcome to know what is the exact concentration of the salt solution that we use in this kind of galvanic cells. But my question is, what happens if instead of using, let's say, copper sulfate, I use salts like copper nitrate or copper chloride? What will happen to the system in that case? I'm not going to use um, electrolytes with the similar uh, anions. What happens if from both anions and cations they are going to be different? Then what will happen to the fate of the system? Instead of, let's say, copper sulfate, I use copper chloride. Assuming that the semi-permeable membrane allows the diffusion of the chloride ions. Think about that as well. So I mean, so the major reason why I am giving these things is because here you can try to vary so many components and their variables, that you can come up with the different possibilities of what will happen to the system, because there are so many different components. That is the reason I said any kind of these electrochemical cells that you take, is indeed a subject of study over decades. If you see batteries, their research has been happening for almost decades after decades, but still we do not have uh, what do you say, kind of a particular battery which can actually power which can be actually used up for a grid level powering systems. We have done a lot of developments, a lot of major developments has been done, but even though so many developments have happened, but still these kind of batteries cannot be, still limitations are present and we cannot completely use them as an alternative to the other kind of energy resources that we currently use. We cannot use batteries still in electric vehicles because of the there are other kind of limitations to them, but even though they have my major thing is, even though they have been a system for study for so many decades, but still so many challenges are persistent. That typically is because every single component in them is indeed a research area. So many things you can vary and change and play around, and you never know which one will give what kind of results to you. So have a think about this also, of what happens if we use different kind of anions to that particular system instead of copper sulfate, copper chloride. So moving to that, after that, question 3. For a reaction to be spontaneous, the delta G, that is your Gibbs free energy of a particular reaction, should be positive, negative, or it is totally unrelated to the spontaneity of a reaction. Delta G must be negative. That is correct. So the okay, delta G is nothing but it's basically the work done on the surroundings, and the decrease in the Gibbs free energy typically represents that the reaction is going to be spontaneous. That's fine. But so my next question in addition to this is, if delta G is negative, or let's say you take a galvanic cell, what should be the potential of that particular cell for that electrochemical reaction to be spontaneous? Delta G should be negative, I get it, but what about the the you can say EMF of the cell, or the potential of that galvanic cell, E, the value of E, if you see, like you have the reaction, right? um, Let me just write that here. Delta G is nothing but minus NF times E. E is nothing but it's your voltage. So if delta G is going to be negative, what should be the value of E for that particular electrochemical reaction, or yeah, for that particular electrochemical reaction, or that for that electrochemical reaction to be spontaneous? E must be positive, because you have so delta G should be negative. So minus so I can write it this way: delta G should be negative. That means minus NFE. So N is nothing but the number of moles of electrons that gets transferred. F is the Faraday's constant. What is 1 farad is, what is the value of the Faraday's constant? And E is your voltage. Value of the Faraday's constant. 96,500 coulombs, or if you want to be very precise, then the value will be equal to 96490 coulombs. So minus NFE should be less than 0. So that means NFE should be greater than 0. Let me just change this. So N and F are positive values because number of moles cannot be negative and Faraday's constant is a constant that cannot be negative. So E must be greater than 0 for a particular electrochemical reaction, or for an electrochemical reaction to be spontaneous. So I hope there are no doubts related to these three questions that we discussed now. If you have, please feel free to ask, or otherwise we can move towards the next one. Question number 4. In galvanic cell, the dash of a chemical process is converted to electrical energy. Oh, sorry. Any answers? Yes, anyone? Chemical energy, okay. Obviously, it's not going to be magnetic energy because that does not make sense. Universal energy, there is no, I mean, that is also not going to be correct. Whether is the answer chemical energy or free energy? Just now we discussed the question number 3. So here if you see, what is delta G? Delta G is minus NF times E. So delta G is also means that it is the work done on the surroundings. So as per classical thermodynamics, work done on surroundings. So, okay, just a second. Then let me just take this there. Oh, so delta G is the work done on the surroundings. So that can be represented as work. Work in terms of electrochemical, the work done to move a charge from one point to another point can be written in terms of QE, and Q is nothing but, you can also represent Q as, you can write work done on the surroundings, so that is minus W. Work done on the surroundings, the convention is it should have a negative sign. So can we write it this way? So here that delta G, that is your Gibbs free energy of that chemical process, is what is actually driving your electrical energy, and that is what is that's what gets represented in the form of E, your volt. So it is the free energy of a chemical process that gets converted to electrical energy. I hope there is no, if you have any questions, please let me know related to this question. As such, from the surface, if you see, it is the chemical energy that gets converted to electrical energy. But then, to be very specific, if you want to say, then it is the free energy of that chemical process which is going to get converted to chemical energy. Sorry, into electrical energy. Before going towards question 5, 6, 7, 8 and 9, let's do this question 10. I hope there are no doubts related to the first 4. If you have anything, please let me know. Otherwise, please solve the question number 10. Calculate the standard Gibbs free energy for the following galvanic cell reaction at 298 Kelvin or 25 degrees Celsius. This is the standard galvanic cell reaction, and take the standard cell potential E naught or E of that particular cell as 1.10 volt. Based on that, calculate the standard Gibbs free energy delta G, and let me know what's the value. minus 2.3 kilojoule. Is the units correct? The value is fine, is absolutely fine, is absolutely correct. But what about the units? Oh, oh. Yes. It is minus 20, sorry, minus 212.27 kilojoule per mole. So the value of farad I'm going to take here as 96500. So it totally depends on you. You can either choose the this approximate value or the absolute value, and E is given as 1.10 volt. What is the value of N? 2. Because here two electrons are transferred. If you see this reaction, you have two electrons which is going from anode to cathode. There are two moles of electrons which is flowing from anode to cathode. So N value is 2. So if you calculate that, then I think I should take this a bit down. Delta G will be minus 96500 times 2 times 1.10, that will come around minus 212.3 kilojoule per mole. So this is the way to calculate the standard Gibbs free energy for any particular galvanic cell reaction, provided the standard cell potential is known. So if any of you have any questions related to this, please let me know. Or otherwise, we have two more questions and then we can wind up for today. Question 7 and question 8. Because I hope you will know the answer for question 5 and 6. Question 6 is okay. Let's see for question 5 and 6 quickly. In an electrochemical cell, say galvanic cell, oxidation occurs at dash and reduction occurs at dash. Where does the oxidation occur and where does the reduction occur? So oxidation will occur at the anode and reduction will occur at the cathode. But will it change in case of an electrolytic cell? In an electrochemical cell, it's correct. But what about an electrolytic cell? Will there be any change or will it remains as the same? Same, yes. So oxidation and reduction, no matter whether you take an electrochemical cell or an electrolytic cell, oxidation will always happen at anode and reduction will always occur at the cathode. This is like a thumb rule which you can remember, which will not change forever. So that's fine. Question 6. In a galvanic cell, electron flows from anode to cathode, cathode to anode, depends on the electrode used, and none of the above. Yes, I mean, we discussed throughout. So I think this question is quite simple, very simple. So this electrons will flow from anode to cathode. Now, if I ask in a galvanic cell, electric current flows from anode to cathode or cathode to anode, of course depends on the electrode used is wrong. In a galvanic cell, if my question is in a galvanic cell, electric current flows from anode to cathode or cathode to anode. Yes, anyone? So previously the question that I asked, I mean that is asked in the question was electron flow. Now I am talking about electric current. Will it be same from anode to cathode? Inside cell it will be from cathode to anode, because the direction of the current by convention is opposite to the flow of electrons. So that, please remember this in mind. Flow of electric current, the direction of electric current is opposite to that of the direction of electric flow of electric charge. This is by convention. Now last two questions. In a representation of the galvanic cell, what we discussed right now, what does that one vertical line represent? That is your question 7. And question 8 is, what does that parallel two vertical lines represent? Yes, so answers one. Seventh one is C. Yes. So the one line is nothing but it's the interface between the electrode and the electrolyte. So seventh one is C. That makes sense. And eighth one is the two vertical lines. So something that actually means it is separating the two compartments. So somebody has said 8 is D. So whether everyone agrees that 8D is correct or it will be something else. Aqueous solution here, it typically means that the electrolyte solution. 8D, one of the audience have told the answer that 8 is D. Whether everyone agrees, interface between the membrane and the aqueous solution, that is the electrolyte solution from the cell compartments, it should be. Yes, anyone with any other answers? Here, if you see for these kind of galvanic cell reactions, we haven't represented the state. So, whenever you happen to write any kind of electrochemical cell reactions, it is always advisable to mention their physical states as well. Then it would be far more easier for anyone to understand. For example, if you take a look at this one, here the zinc is in the form of a metal, so that will be in the solid state. Zinc 2 plus will actually enter inside the electrolyte, so that will be that will be in liquid, or you can say aqueous. Copper 2 plus also will be in aqueous, and copper is a solid, so that is will be represented as S. So it is better to mention the physical states as well while writing any kind of electrochemical cell reaction. So question 8, the answer is D. It is the interface between the membrane and the aqueous solution from both apartment of the cell. You can better to word would be interface between the membranes and the anodic and cathodic compartments. So, do you have any doubts related to what we have discussed today? Question 9 is simple. It's just asking which one is the oxidizing and reducing agent. So, I hope you will be able to answer that. If you have anything to discuss, I mean, related to the questions, then please feel free to ask me now. Or otherwise, we can conclude our session for today. That's what something that even I asked. I mean that question that I put forward, because since this galvanic cell is going to be a closed system, we are not going to add additional materials to that. So so over the period of time, what is going to happen is zinc is going to get depleted and copper is going to become thicker and thicker. So what's going to happen to the fate of the system? That's what I asked. So let's discuss this in the next class. So next class we have few questions to discuss. It's like something which is kind of we need to think. So the first one would be what will happen over period of time. Second thing is um, what happens if I remove the membrane between the galvanic the membrane separating the two compartments of the galvanic cell, removing membrane. Third thing is why I can't use different anionic electrolytes, like different electrolytes altogether, even in terms of different anions as well. There was another thing was related to this osmotic diffusion. So let me stop sharing. So if you have no doubts, then I mean, apart from these questions, I have noted them down. So let's discuss this in the next session, because these kind of questions requires us to think for a little bit longer. So I want everyone to actually think about these questions so that we can have a productive discussion on them. Apart from that, I would like to know that do you have any comments related to the live interaction session that we are presenting, because this course is going to be very short. It's just going to be for 4 weeks. So in case if you have any comments or feedbacks related to the way this live interaction session has progressed, then please let me know. You're welcome to let me know in the comments, or you can unmute yourself as well, then speak here. Anything that you would like to change, like reduce the concept discussion time, because I think today also it took approximately 50 minutes or so. Reduce that time and then give more time towards this question solving. Any kind of suggestions or feedbacks, or the pace at which we are discussing the things. Okay, yes, more numerical practice. Okay, I'll note it down. Other than that, any suggestions and feedbacks from your side? Okay, so in case, so of course, if you have any other feedbacks or suggestions, then my mail ID will be provided along with this presentation. So you're welcome to email your suggestions to me, or even if you have any doubts, then feel free to ask me via the email or in the course Q&A session. Some of the questions we will try to answer it in the class so that it will be helpful for the entire audience as well. Other than that, in case if there are other minor queries, then I will try to answer to them as soon as possible via email, or again, as I said, you are always welcome to post those questions in the Q&A sessions. So thank you everyone for joining today's live interaction session. I also thank Professor Mainak Das for giving, and the NPTEL team for providing me this opportunity to interact with you all. in this Saturday afternoon. Our next live interaction session will be on 31st of January, same 5 p.m. to 7 p.m. So I hope to see you all there. Till then, enjoy the course and thank you. Have a great weekend and bye.